proves that the concept really works. Okay, so we talked about noise floor modulation, we've talked about small signal accuracy. I'm going to talk about transients and the WTA filter now. So here we go on to M-scalars and that kind of thing. So why are transients important? What is a transient? Transient is when the signal suddenly changes. So you're listening to silence, that initial crack, that's a transient. Transients are very, very important. The brain uses transients in terms of a lot of different psychoacoustic ways of finding things out. One of the important things is to measure the time difference between the left ear and the right ear. And what the brain has got is something called the interaural delay. And these are a set of neurons in a chain connected from one ear to the other ear. And each neuron has got a delay of about 4 microseconds. Some people put it at 6, some people put it at 10, some have said 4 microseconds, but it's 4 to 6 microseconds. Each one's got a little delay. When you connect the delay together, when the signal hits one neuron from the left side and the right side, the neuron will fire. And they did this experiments with cats in the 1950s where they anesthetized a cat, opened up its skull and probed into these nerves, and they actually found these neurons firing. So we know that this thing physically exists. Didn't do that with humans, that wouldn't be a good idea. What we do with humans is that you just listen to the left ear and the right ear, you feed a phase signal and you adjust the phase, and you find out where you can hear it. Can you hear the shift in phase? So we know this exists, it's about 4 microseconds. And it's one of the perceptual cues that you use for hearing information from left to right. That implies 4 microseconds timing that the brain is working to about 250 kilohertz. CD is only at 44.1 or 22 microseconds. So the brain is working to a higher speed than CD is working to. That's an important factor because it explains a lot about why high definition and why the WTA filter works. Transients is also vital for bass perception. So if you look at the performance of the ear is not very good as a transducer for bass. It rolls off, it's got a lot of distortion, and what the brain does is it calculates from the output what the actual bass is doing. And it looks at transients. So if you remove the transient information, in other words, the sound of somebody plucking the bass guitar, it becomes more difficult to hear the pitch of a bass guitar. This is something that they've done, psychoacoustic tests, remove the transient information, you can't follow bass pitch. Timbre is also very, very important. Again, take a trumpet, take a piano, obviously they sound very, very different. If you remove the transient information of a trumpet and a piano, it becomes very difficult to tell the timbre between the trumpet and the piano. You can't tell the difference in the sound. So transients are very important for timbre as well. So why is digital audio so bad? Why is there such a big problem with digital audio? Problem is the reconstruction of transients in terms of the timing accuracy that we need. CD's 22 microseconds. We know that the ear brain will work to 4 microseconds just for the interaural delay. What I found is that timing errors will create a big subjective impact. And you may say, what do you mean by a timing error? Now, when you put a signal through a regular DAC, the timing of the transients will either be slightly too early or slightly too late. This uncertainty is constantly moving backwards and forwards, and it depends upon what happened in the past, and it depends upon what happens in the future. So all these things modulate the timing of the transients. When the brain sees this uncertainty, it gets confused. And when it gets confused, you can't perceive bass properly, you can't perceive timbre properly, you can't perceive pitch. And also instrument separation and focus becomes worse. and you can't perceive where things are located in space. Now the problem with this transient uncertainty is down to the limited processing that's available. I can illustrate this timing problem. This is just a very simple illustration, just to show you what's going on. Imagine that we've got a sine wave transient. So this is a 20 kilohertz tone burst. So this is the start of the transient. And if we sample it at that point there, in the digital data it becomes 0. The next sample point will be here, and then we'll get that. And the next sample point will be somewhere down here, and you'll get that. And the digital data looks like this. So it doesn't actually look like the original sample, the original analog signal. If you pass that digital data into a simple filter, like a NOS filter, an IR filter, an MQA filter, you will end up with the digital data just looking like this. So it loses the original transient information. But if you put that into something that's called a sync function filter, which has an infinite amount of processing, it will perfectly reconstruct the original 20 kilohertz tone burst. What's amazing is it will reconstruct the initial pulse that didn't exist on the digital data. This has been proven. This is basic sampling theory. And we know that this is a fact, is how the maths works. So, filter algorithm, the algorithm itself that is used to reconstruct the filtering information. The algorithm itself has a big difference on sound quality. And when I first started playing around with this, going back to 1999, when I had my first WTA filter, I started off with a long tap length filter. In those days it was 1,000 taps. Conventional filters, only 100 taps. 1,000 taps was the maximum I could do with the FPGA technology that you had available. But what I found was that if I changed the algorithm, I would get better reconstruction of transients and better sound quality. And that led to the WTA algorithm. As time has gone by, the algorithm has improved, tap length has increased. I changed the algorithm, and the algorithm is all done by a mixture of two things: theoretical knowledge about what's going on when you're using an interpolation filter, about trying to reconstruct the transients as accurately as possible with a finite amount of processing, and more importantly, listening tests. Everything is done by optimizing with listening tests. And there's been hundreds and hundreds of different listening tests to try to make this WTA filter more accurate in reconstructing the timing information. What I ended up with was a 256 tap length WTA filter sounded better than a 2048 tap using a conventional algorithm. So I got a 10-fold improvement in how it reconstructs it without increasing the tap length. So that's really important. One final point. Today, the algorithm is extremely close to an ideal sync function filter. A sync function filter will reconstruct it perfectly, but my algorithm, the WTA algorithm, half of the coefficients are identical to an ideal sync function. Normal filters are very, very different from sync functions, and there's something quite strange about the sound quality of when you're listening to a sync function, in that it sounds more natural and sounds much better. Even though when you analyze it, it shouldn't make much difference, it does make a difference to the sound quality. Getting it to sound like sync makes a big difference. So, tap length history. DAC 64, we're looking at 1,000 taps. And then QBD 76, we're at 18,000 taps. Hugo 1, 2013, 26,000 taps. And then Dave, 164,000 taps. Every time I increased the tap length, sound quality got better. Bass definition was better. And we know that because transients and bass is important. Soundstage got better, and that's obvious because you were locating instruments much more accurately in space. The instrument separation and focus is better, and the timbre is better. Again, this is all because of your transients, your timing information is being, the uncertainty, the inaccuracy is being reduced. And of course you can perceive the starting and stopping of notes much more accurately.
Rob, can I ask a question? Where does Mojo fit in with all that?
Right, Mojo is, we say it's 500 times more processing power. We haven't actually published the tap length. It's actually 38,000 taps. So actually Mojo, for a £400 device, is extremely competent in terms of its ability. You know, the reason why Mojo sounds so damn good, so musical, because of the processing that's gone inside it. Right, okay.
So you didn't mention the tap length there for the TT2 there, did you? So
No, TT2 is 98,000.
okay.
Yeah. Yeah, okay. So my Mission Impossible. I studied electronics as a science degree, so we wasn't doing electronic engineering, but electronics as science. That meant I spent more time on theory, sometimes a bit too much theory, but that's another subject. And I also spent time about physiology of hearing, because my digs were very close to the psychology lab. And so in the weekends I go into the psychology lab and read up about physiology of hearing and all these tests that they were doing. And I realised that transients were very, very important. I also realised from Shannon interpolation theory that conventional filters would create timing errors because of this uncertainty that we would do that. And that these timing errors would be audible, because I knew from psychoacoustics that timing was a very important psychoperceptual cue. And then I wrote on the back of an envelope, you know, let's get 16-bit performance from CD. What tap length do we need for 16-bit? And it turned out to be nearly 1 million taps. These were the days when state-of-the-art microprocessor was 20 megahertz, 2K's worth of memory, and 1 million taps was clearly going to be impossible. You couldn't even do it with a supercomputer. It would be impossible. So my gut feeling was that digital would never sound good until we got to 1 million taps. And that was why digital in the 1980s sounded so awful and would never be recoverable. So why is 1 million taps so important? Well, this is the response from 100 samples of a sync function. As you can see, it decays away to 0, both in the past and in the future. What I thought was, well, let's make this decay away to less than 16 bits. When you get below 16 bits, then you know you've got your output's going to be accurate to 16 bits. And that happens when you hit about 750,000 taps, when your sync function decays below 16 bits. And then you can forget about the smaller numbers because they're below 16 bits. And that gives you 16-bit accuracy. So what this means is that with the M scaler, because the sync function is the same as 16-bit sync function, it's actually 16.7 bits, we are reconstructing to better than 16-bit. So we're recovering the original analog signal to a better accuracy than 16 bits. Hugo M scaler. This has the full 1 million taps, and it's got multiple inputs, galvanically isolated USB, 2 BNC inputs and 2 opticals. Dual BNC outputs, single BNC outputs for feeding with other DACs, and an optical output. That was for there when you want to do your own recordings to convert 44.1 into 176.4. And it's got adjustable sample rate outputs, and it's got a pass-through mode, so you can easily hear the difference of the M scaler being switched in and down. It's got a video mode for lower delay, and it's got auto mode, so that's quite convenient. So when you're just plugging different things in, you can just run it in auto mode. Remote control, DX for future products coming out in the next few years, and it powers from 9 volts to 15 volts. You can actually use a battery backup. So on flights I use an M scaler with a battery, and it normally leads to interesting conversations with the air stewardesses, which we end up talking about music. But once you get used to the sound of the M scaler, you can't live without it. So on a 10-hour flight or a 13-hour flight, I have to have my M scaler with me. And that's the reason why I put 15 volts as the input, so that I could use a standard laptop battery backup. So we've talked about a million taps. We've talked about being able to recreate the original analog signal that was in the A to D converter to a better than 16-bit accuracy. What does that give you? What it gives you is a kind of musical link to the original recording. And in terms of musicality, it's like you're actually there. And I've played lots and lots of 1960s recordings. 1960s recordings seem to sound the biggest difference when using the M scaler. And you connect to the original performance. And it's quite uncanny how it does that. Also, you get much better pitch reproduction, melody, timbre, and space. The other curious thing is that you can be listening, and then suddenly a loud instrument comes in, and it really hits you hard. A very powerful instrument. And yet you can have other little quiet instruments playing in the background, and they're still playing in the background, and they don't cross-modulate one another. And that used to puzzle me as to why this perception of instrument power was so much more powerful with the M scaler. And then I realised it's just simple modulation. With the conventional filters, you've got the actual signal in the future and the signal in the past modulating the timing. And when you remove that modulation in the timing, suddenly instruments have such a vibrancy and a sense of power that can really be quite breathtaking. And it's that lack of modulation, or getting it back to 16-bit accuracy, that's important. But the big factor is the emotional connection, the musicality, which is what I was talking right at the very beginning of this talk. That's what I'm trying to do. I'm trying to get emotional when I listen to music. I want my spine to tingle. I want tears to happen for engaging music. I want to be involved. And that's what the M scaler does for me. So it's been quite an interesting journey over the last 35 years, going from it's completely impossible when we need it to actually being able to reproduce this. So this last couple of years has been very exciting for me in terms of that. The other thing that's been very exciting is my passion for listening to more and more music is increased. And I'm finding I'm buying a lot more music. That started with the Hugo. It's just gotten bigger with the M scaler in terms of wanting to listen to more and more music. And you get addicted to music. And you want to listen to more and more and more, which is why I go to the trouble of carrying an M scaler in my bag when I'm on flights. So this is the time now for questions. I'm afraid I've gone over the time a little bit, but please ask whatever questions you like.
So I suppose the very obvious one is, what is your portable setup?
Well, it's,
what else are you running?
Yeah, it's a Hugo. I'm getting my bag, but of course my bag's in the car. I've got this bag. If I'm flying business class, it's fine. I just put everything onto the shelf, and I plug the mains in, and you've got the M scaler, you've got Hugo. I use my remote control, my mobile phone as music source, plug it in, and Mr. Speaker's headphones, and I'm happy. If I'm flying economy class, I put everything in the bag. So the M scaler fits in a little pocket in the bag. Battery backup fits in there as well. It'll run for 2 hours. It gets very hot, probably about 45 degrees C, so you don't want to touch it too much after you've done that, but it works fine. But it's once you get used to the sound of the M scaler, you just can't live without it. So it's quite important. I was actually quite shocked the other day because we had a show, and we wanted to borrow my M scaler, and I was watching some video stuff. I thought it's only video, I don't need the M scaler for this. Listening on headphones and watching this, and suddenly I thought, wow, this sounds so bad. The other curious thing about the M scaler, and this really is puzzling. first time I heard 500,000 taps, every single time I've increased the tap length, bass perception gets better, timbre variation, soundstage from left to right becomes more accurate. Depth never changes. That's always fixed. And depth is, as I've talked about before, small signal accuracy, amplitude on linearity, all that kind of stuff. Nothing to do with the timing of transients. But the 500,000 taps, bang, the soundstage just opened up. And then when I went to 1,000,000 taps, you could hear an extra increase in the soundstage opening up. And it's actually a puzzle as to why going from Dave's 164,000 taps to the M scaler 1,000,000 taps, why the soundstage opens up. Because I don't understand that. It doesn't make sense from an engineering point of view. It doesn't make sense from our perceptions of sound. The only thing I can think of is that the M scaler is looking at about 1.3 seconds of music. So it's doing its calculations based on 1.3 seconds of music. That's about the RT time period of a concert hall. So RT time period is reverberation time.
Yeah.
So that will be a second or 3 or 4 seconds for a big concert hall. And there's something, I think there's maybe something to do with that. But that's the thing that really surprises you. When you hear the M scaler, it just opens up. So I was listening to this thing without the M scaler, and it just sounded flat. And all the other things as well, but it was quite shocking going backwards. Because that's the first time in the last 2 years I've actually not listened. I've always had M scalers. I've not listened to any length of music without it. Sorry, I went on a bit there.
Don't want to keep asking questions if anybody else can. But obviously you've talked a lot about reproduction of sort of sound scales from, I guess your reference was concert halls and,
Yes.
and live music of unamplified music.
Yes, yeah.
Probably a lot of people I think in here, and probably yourself, probably listen to a lot of music which is generated with amplified instruments. Discuss.
A lot of what I listen to, I mean, a good 10% of what I listen to, in fact recently I've been listening to a lot more, is electronic music, which has never existed outside of acoustic space. Again, you can hear the effect of the acoustic opening up. It's artificial reverb, and they've added artificial depth and located the instruments completely artificially, but you can still hear that. Electronic music is actually very, very good because it's unnatural in one sense, because you can set it so that there's no reverb, and when it shuts down, it stops. Normal instruments, you pluck a string, it decays away, and takes a long time to decay away. Electronic music, you can make it stop immediately, and that starting and stopping, you can perceive that really accurately with the M scaler. That's why I talk about starting and stopping of notes. When I'm thinking of stopping of notes, I'm thinking about electronica music, where the bass drum boom, 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 stops so sharply, and you can perceive that. Live bands. A live amplified music sounds pretty awful in a lot of ways. Completely flat. There's no soundstage from a major concert hall when you've got 50,000 people listening to it. It's completely blurred from left to right. When you listen to the mix straight off the mixer on headphones, then things are really accurately focused. But when you listen to it actually through the PA speakers, it's pretty awful. What it does have is that immediacy and that sense of power. I was talking about instrument separation and focus, I was talking about instrument power. When they cut in with a bass guitar or they cut in with a normal guitar, that cutting edge you can really perceive really well on a live concert. So live concerts aren't very good, amplified live concerts aren't very good at appreciating hi-fi or transparency. But there are aspects about it that you, like the speed, like the instrument separation, like the power of instruments, that you do get on a live concert, which the M scaler helps to reproduce.
And where do you go, obviously, with pre-recorded music of that type? Like, you obviously mentioned about you don't really understand what the original sound is like. Well,
yes,
we'll take a standard 5-piece band or a 4-piece band or whatever. They're probably all going to record their parts separately anyway.
Yes,
so,
of course.
So how?
That's where
Yeah.
you're making assessments on whether you've made a fundamental improvement based upon looking at variability. So you check for timbre variation, you check for space variation, you check for detail resolution, instrument separation and focus, and I go through all those different parameters and assess each individual one. So that situation I was talking about, RF noise coming in,
Yeah.
that can create the artificial impression of transparency because things sound brighter, they sound etched. You've got noise pumping up and down with the signal. That noise is bright. So that artificially enhances the sound. The thing is though that you find that even though you think the transparency is better, the detail resolution is better because you've got this noise pumping up and down with the signal. When you listen to the timbre of each instrument, you'll find saxophones also sound brighter. And that's not right. Saxophones should sound rich and dark and smooth. So the minute you listen to and check for timbre variations, you'll find that the detail resolution seems to be better, but the timbre variation is worse. And that will be a red flag to tell you there's something else that's going wrong. One of the benefits that I've got is that my listening tests are actually most of the time about understanding an engineering variable, a distortion or something that I know about, and then listening to it. And I can normally do it so that I can just change that particular variable, like the noise shaper thing, for example. You're just adjusting the performance of the noise shaper, you're just changing the small signal accuracy. By listening to that and seeing what the effect is, you can accurately control what that variable is and how that's making a difference to sound quality. So noise level modulation, I can do the same thing. Distortion, you can do the same thing. You can measure it, you can define it, you can then do listening tests. So my listening tests are very, very specific. That makes life a lot easier because if you know the technical, what's going on behind it, it's actually less likely you're going to make mistakes. But mistakes does happen, and too many people in the audiophile business like distortions, or they think the distortion is making it sound better, but it doesn't. It doesn't actually work because your musicality will get degraded, or you'll end up with a situation where you're listening to your hi-fi for an hour and then turn it off because you've got listening fatigue stepping in.
Yeah.
Listening fatigue is something really important, and it's.
No, listen to MP3, instantly.
Oh yeah. I mean, 10 years ago, I wouldn't listen to my system for more than an hour, and I just turn it off and do something else. Now I can listen for 12 hours on a flight, get off the plane, go into the hotel room, listen again, and I never could get that. Even 5 years ago, I could never get that level of performance. Things have just moved on so much in the last 5 years.